Welcome to GPU programming. Today, we'll explore how GPUs and CPUs work together to execute parallel code. We'll focus on understanding their roles, how they interact, and how parallel work is structured and executed. Let's first understand how CPUs and GPUs coexist in the same system and work together, rather than thinking of them as competing architectures. Each has a distinct role, and their interaction defines performance and efficiency. The CPU is the system's decision maker. Built over decades, it runs the OS, compiles code, manages memory, and controls execution. Every program starts on the CPU. When heavy parallel work appears, the CPU decides to offload it to the GPU, prepares the data, launches the work, and synchronizes the results. GPUs accelerate computation, but CPUs orchestrate the entire process. Once the CPU delegates work, the GPU needs only a small set of instructions to proceed. What data to read, where that data resides in memory, where to write the results, and the program that defines how the data should be processed. With this information, the GPU executes the computation independently and returns the results to the CPU when finished. The interconnect is the physical and logical link between the CPU and GPU. Technologies like PCIe Common and NVLink on platforms such as IBM Power and NVIDIA Grace Hopper define how commands and data can be exchanged, setting the raw communication capability of the system. A single source contains both CPU control logic and GPU computation. This helps programmers maintain one clear and consistent code base. The compilation toolchain separates the source into independent CPU and GPU compilation paths, ensuring each processor receives optimized instructions. In CUDA programming model, the work is organized into clear hierarchy: threads, warps, blocks, and grids. Thread is the fundamental unit of execution. Each thread performs a single, defined operation on a portion of the data. A group of 32 threads executes together as a single hardware unit. This unit is called a warp. All threads execute the same instruction at the same time, while operating on different thread indices and data. Threads in a block can share fast on-chip memory and synchronize. Blocks typically contain hundreds of threads. The CPU schedules blocks across GPU cores, mapping them to available resources. A grid contains many blocks, potentially thousands, executing independently. The CPU manages grid launch and data flow between host and GPU memory, ensuring all work is dispatched correctly. But how does each thread know which piece of work to do? Through its unique identity, determined by its position in the grid and block. Block index times block dimension plus thread index. This maps every thread to a unique position in the entire grid, enabling threads to access distinct data elements. Communication between threads follows strict rules based on the hierarchy. These rules affect how shared memory and synchronization can be used. Within a block, threads have powerful capabilities. They can use shared memory, a fast on-chip cache. They can synchronize using sync threads. They can coordinate efficiently for reductions, scans, or data sharing. But across blocks, completely different story. No shared memory access, no synchronization primitives, no guaranteed execution order. Blocks are intentionally isolated to allow flexible scheduling. This is fundamental to CUDA's design philosophy. Blocks must be independent. This allows the GPU to schedule them flexibly across different streaming multiprocessors and enables scalability without inter-block dependencies. And that's the CUDA thread hierarchy. Understanding this architecture is essential for writing efficient parallel code. Design your kernels to exploit within-block cooperation while keeping blocks independent, and plan data movement carefully. This systematic approach ensures predictable performance and resource utilization.